Rational functions are functions given by rational expressions in the independent variable. So just to remind us, a rational expression is pretty simple. It's a ratio of two polynomials. So f of x is equal to, let's say, px divided by qx, where both of these guys are polynomial functions. So these are polynomials. So this is a rational function, unsurprisingly. So we've already thought about the algebra of rational expressions in a reasonable amount of detail. What we want to do now really is to think about the properties as functions. So just some quick examples. X squared is an example, of course, right? This may not look it, but it definitely is because of the fact we could have x squared divided by 1. So a polynomial is an example of a rational function. But you could have things which aren't polynomials. So for example, 1 over x. So 1 over x is not a polynomial because it would be written as x to the minus 1, which is negative. And in polynomials, the powers all have to be non-negative. One that's really obviously a rational function would be 3x minus 1 divided by, I don't know, x plus 3. So for other core functions, we take the time to work out graphs, domains, ranges, all these kind of things, at least when we can. For rational functions, it's actually much more difficult. So here's a fact that we can't really ignore. So the properties of rational functions are too varied to give a succinct description. So the properties of rational functions are too varied. To give a single succinct description of them. So that's annoying. It's a bit like polynomials of higher degree, right? We can't just completely pin everything down. It really depends on the circumstances. So typically, things that really vary are range, the increasing or decreasing intervals, boundedness, the symmetry, odd or even, and one-to-one. All of these properties, generally speaking, are very difficult to determine for a rational function. So really what I'm going to do is focus on a few of these properties. So I'm not going to do the usual business of writing down kind of a list of what is the domain, what is the so-and-so. I will talk about kind of two things, I think, which are worth thinking about. The first I'm going to think about, well, I'm going to do them both together, actually. I'm going to think about the x-intercepts, so the positions where the function is 0, and I'm going to think about the domain. These two things are a bit more tractable, I think. So for x-intercepts, well, what can we say about this? Well, f of x is equal to 0 if and only if what? So this is pretty straightforward. My ratio is equal to 0. And that's if and only if what? So one must be careful, right? This is if and only if two things have to happen. Px is equal to 0. And it's important here, Qx can't be 0. If Qx was 0, it wouldn't make sense. 0 over 0 doesn't make sense. So what does that mean? Well, finding x-intercepts now is just going to be the process of finding the zeros of polynomials. So looking at this, I can kind of see we're going to need to find the zeros of px. And I suppose once we find them, we need to check they're not the zeros of qx, otherwise we'll run into problems. Now this doesn't look immediately related, but it is closely related to domains. Remember what the convention is. If I give you a formula for something, the domain is all values of x such the formula makes sense. So the domain in this case of my rational expression px over qx, well, clearly there's only one issue, right? The only issue is dividing through by 0. Polynomials make sense for any x, but the problem is I could end up with a ratio with 0 on the bottom. So this is going to be all x such that qx is not equal to 0. So again, these look different, but at the same time, they're very related, because finding the domain is going to require us to determine where qx is non-zero. So that basically means we're going to have to find out where qx is equal to 0. So the same story. So for finding domains, where am I? So we're going to need to find the zeros of this. So even though in general x-intercepts and domains are very different things, for rationals they have a very similar process of determining things. And I should say this is because we can't divide through by 0. Okay, so we can't divide by 0. Can't divide by 0, of course not. So it's similar when it comes down to it. So I think what we should do is take a couple of examples and go through them quite carefully. And there's going to be a few things I'm going to do which are going to be a bit hand-wavy. And what I mean by that is I'm not going to fully justify them. So really, to get your hands dirty with rational functions, you need to develop the tools of calculus. So we can't go into a huge amount of detail, but I can illustrate a few really important properties which will be useful to know when you go into calculus. So let's do some examples. So let's do the following. Let's do f of x is equal to 1 over, we'll do x squared minus 1. So what have I got? On top I've got my px, that's just 1. And on the bottom I've got my qx, and that's equal to x squared minus 1. So let's do domain first. Why not? Let's do domain first. In fact, no, let's do the x-intercepts. I did them first, didn't I? Okay, so first of all, px is equal to 1, right? It's the constant function 1. This is not equal to 0 for all x. Of course. So this means there is no way of having any x-intercepts. The numerator can never be 0. There can't be any x-intercepts. So now let's think about setting q to be 0 to find the positions where potentially we have problems with the domain. So this is if and only if x squared minus 1 is equal to 0, which is if and only if x plus 1 times x minus 1, difference of two squares, is equal to 0. By the 0 product property, either x minus 1 or x plus 1 is 0, or x minus 1 is equal to 0, if and only if x is equal to what? X is equal to minus 1 or 1. So there are two places where it goes haywire. So putting this together, and it doesn't really matter what happens with the p, because if q is 0 on the bottom, who cares what p is on top? It doesn't make sense. 0 over 0 doesn't make sense. 0 on the bottom, full stop, it's over. So this tells you what the domain is equal to. So I'm going to write it in interval notation after I've written it in this form. So this is all x such that x is not equal to, well, I'll do plus minus 1. So in interval notation, which isn't always necessary, but I'll write it just as a bit of practice, minus infinity to minus 1 not inclusive of -1, so it's an open bracket. -1 to 1, not inclusive of 1 because it's an open bracket. Union, open bracket, off to infinity. So it's kind of 3 disjoint intervals if you want. So there are no x-intercepts, and the domain is this kind of combination of 3 intervals. Let me show you the graph of this. Now this is difficult. Like I said, this is not something you can really do without more sophisticated tools from calculus, but I want to show it to you just to illustrate some interesting behavior. So we'll take y, we'll take x. So we basically know there's some problems at -1 and 1. So let's mark -1 and 1. And let's actually do something interesting. Let's draw 2 vertical lines at 1 and at -1. So they should be at the same position. That's about right. Okay, so this is -1 and 1. Well, it turns out if you graph it, it looks like this. And this is not obvious at all. But you have this kind of rather interesting behavior. It kind of does the following. So a strange kind of behavior where it kind of gets really close to these vertical lines as they get closer into 1 and -1 from below and above, and from the left and the right. And this side, it's kind of like this. So again, this is very hand-wavy from a mathematical perspective. It's imprecise because I'm not giving us a really detailed reason why it looks like this. We're just doing it so I can illustrate some of the kind of interesting behaviors. So this is y is equal to 1 over x squared minus 1. And if you want to know, for example, the y-intercept, that's when it's 0. So if I feed in 0, this would be 1 divided by -1, so it's -1 down here. Not that that's terribly important. Okay, so again, we can see there are no x-intercepts. At no point do I touch the x-axis. I might get really close to it down here, but I'm never actually going to touch it. Okay, so this is just important. This is not obvious what I've done. So no x-intercepts, great. I do have these 2 points which are definitely not in the domain, and the way they fail to be in the domain is quite interesting. As my input gets closer and closer to these 2 points, -1 and 1, the outputs of the functions seem to go a bit haywire. So they either get really big and positive or really big and negative. So a situation where this happens is something called an infinite discontinuity. So this is kind of fancy terminology. Really what this is a preview of ideas that you're going to study in calculus in a lot of depth. So called an infinite. But it's quite nice to see them visually now. Discontinuity. An infinite discontinuity. The word infinite because it's just getting massive positively or negatively without bound. Discontinuity because it's something bad has gone wrong, something nasty. Just a picture I think it's worth seeing. Let's do another example. So I really want to show you the incredible variance in the behavior of functions. So let's do the following. So example, let's do f of x is equal to, what should we do? Let's do the following one. Let's do x squared plus 2x plus 1. All divided by x plus 1. Okay, so again, px here is equal to x squared plus 2x, x squared plus 2x plus 1, and qx is equal to x plus 1. So let's go through x-intercepts first. So x-intercepts. Okay, so we've got to check the zeros of p, don't we? So px is equal to 0 if and only if x squared plus 2x plus 1 is equal to 0. So we could rush in with a quadratic formula, but this is a very standard factorization. This is x plus 1 squared is equal to 0, if and only if x is equal to minus 1. Now, at this point you might say, well, minus 1 is an x-intercept, but be careful. However, if I was to feed this in, q of minus 1 is equal to minus 1 plus 1, which is equal to 0. So this implies what? This is not an x-intercept. There are no x-intercepts because it would be 0 divided by 0, which is undefined. So that's a bit subtle, right? You can't do this completely brainlessly. What about the domain? Well, this one's much easier. Qx is equal to 0 if and only if, you've kind of almost seen this already, x plus 1 is equal to 0 if and only if, of course, add minus 1 to both sides, x is equal to minus 1. So the domain is equal to, well, it's everything apart from minus 1. So all x such that x isn't equal to minus 1. It doesn't matter that minus 1 is a 0 at the top. 0 over 0 is still undefined. So in interval notation, minus infinity to minus 1, union minus 1 to infinity. Not inclusive of minus 1. So let's think about graphing this. So I want to make an observation. And I think we've seen this a little bit before when talking about equality of functions. But I want to kind of go through this very carefully because this causes extreme confusion with good reason. So f of x is equal to this guy, isn't it? Nothing terrible about this. And we can factor the top as x plus 1 or squared divided by x plus 1. Now, it's super tempting at this point just to be like, oh, look, I'm going to use the law of exponents, or one of the laws of exponents, and just write this is x plus 1. The thing about that is that law of exponents only holds when the base is non-zero. So at this point, if you want to simplify this, which we desperately want to because it's such an obvious simplification, we need to make sure x plus 1 is not equal to 0. So this thing breaks into kind of two situations. One of them would be when x plus 1 is not equal to 0. Okay, so of course, i.e., this is the situation we're above, x is not equal to minus 1, all good. Then, of course, it simplifies as x plus 1. That's my law of exponents. So if you want to make this super duper clear, this is me just doing what? Well, there are several things I'm doing, but this could just be b to the a divided by b to the c is equal to b to the a minus c. Okay, so that's basically what we're using there as a law of exponents. There are several other ways to do it, but that's a good one. The other hand, down the bottom, well, if x plus 1 is equal to 0, i.e. x is equal to minus 1, well, this is exactly what we're talking about with the domain. In this case, it's undefined. It's 0 divided by 0. 0 divided by 0. So, again, this is precisely because we got 0 over 0 here. So what's the conclusion? Well, the conclusion is the function is incredibly close to just the function x plus 1, that linear polynomial, with the single caveat that it's not defined at minus 1. So it's a really weird example, this. So the conclusion is, so like I said, we saw this in the very first lecture on functions, or the very first video on functions, where I talked about the idea of equality between two functions, when two functions had to have exactly the same domain. So it's incredibly tempting to think that this rational function is the function x plus 1, but there's a big difference. The big difference is it's not defined at minus 1, whereas x plus 1 is defined at minus 1. So the conclusion is we can write this in a piecewise format, if we want, as x plus 1 if x is not equal to minus 1, and it's just undefined. undefined if x is equal to -1. So again, it's very important. This is not the same function as x plus 1. So warning, very close but not the same. Not the same function as just x plus 1. If I write the function x plus 1, I'm implicitly assuming that its domain is equal to all x where it makes sense. That makes sense for any x, including -1. So this is very slightly different. Now what does that mean? Let's think about the graph. Thankfully, we do know a lot about graphs for linears. They're just given by straight lines, and I can see two things. I mean, if I was to graph y is equal to x plus 1, it's slope 1, y-intercept 1. So it's a very straightforward example. So if I'm going to graph this whole thing, what I should basically do is just graph y equals x plus 1, and then remove the problem point. So the graph of my function y is f of x, not x plus 1, should be, well, it should just be basically exactly the same as the graph of y of x, but with a core caveat that it's missing this point here at -1. Okay, so at -1 we're undefined. So basically this is an interesting example. This is a graph which looks almost exactly the same as the straight line, with the single difference that we're missing one point. And I know I'm exaggerating it there with this huge hole. It's not a huge hole, it's just one point being removed. So this is really different, isn't it, right, than the previous case, right? In the previous case, these points which weren't in the domain were crazy. As I got closer and closer in, the graph seemed to go haywire, off massively positive or massively negative without any bound. But here it's a totally different story. -1 isn't in the domain, but as I get closer and closer on both sides, it's not going haywire, right? It's staying very close to this point. So this is given a name. This again is a discontinuity because it's something bad happening, but it's called a removable discontinuity in the sense that I could just add an extra point and it would all go away. Whereas I definitely cannot do that up here, right? There's no extra point I can add in and suddenly everything's fine. It would always be bad. So this is called a removable discontinuity. Discontinuity. Like I said, because you can kind of remove it, you get an extra point. And again, we can see here why there's no x-intercept. It's precisely because of this annoyingness, right? We're kind of removing it almost. No x-intercept. This actually is a good example for several reasons. In a sense, the graph it's crossing the x-axis, isn't it, right? But it's not touching it at any point. It's leaping over it. And an x-intercept is literally a point where it is equal to the x-axis. It's touching it. So this is very interesting. We have two examples which look really similar to each other, just when written down as functions. I mean, you look at this and you look at the previous guy, this guy. I mean, they're both rational expressions. It doesn't feel like there's a huge difference between them, but there's a massive difference between their graphs. Enormous. So I think it's a good plan to take the time to work out why there's such a difference between them. And this is something we can certainly do with our pre-calculus knowledge. Like I said, to really understand rational functions, you're going to have to learn calculus. But before then, this is useful things to know. So here's the question I want to ask. I mean, why the big difference? Why the big difference? So let's make some observations, shall we? How did we go about all of this? Well, we factored as much as we could, didn't we? We really factored the top and bottom as much as we could. So observations. So the first guy we had was this. 1 over, what was it, x squared minus 1. And the top doesn't really factor. just leave it as 1. This is x minus 1 times x plus 1. And the second guy was what? It was x squared, was it plus 2x plus 1 divided by x plus 1. And here when I factor everything, I get an x plus 1 squared divided by an x plus 1. So let's take a moment to think about, let's say, the problem I had at minus 1. So minus 1 was a problem for both examples, wasn't it, right? In the first case, it was this weird infinite discontinuity. In the second case, it was a removable discontinuity. Is there an obvious difference? Well, let's just observe a few things. So first of all, minus 1 being a 0 is to do with factors of x plus 1. And at the top, there's 0 factors of x plus 1. And on the bottom, there's exactly 1. Yeah? So there's more factors on the bottom than the top. Here, though, it's the other way around, isn't it? This guy, there's 2 factors. Of x plus 1. And there's 1 factor on the bottom. One factor on the bottom. So what's the obvious difference? Well, the obvious difference is there's more factors. There's strictly more factors in the denominator in the first example. And there's more than 1. Well, there's more on top. So this actually is part of the general story. If I have a 0 of qx, so something that's going to cause a problem in the domain, if I factor out, let's say, x minus alpha as much as possible from both the top and the bottom and count which has more, I can determine if I'm an infinite discontinuity or a removable discontinuity. So again, we're not proving any of this, it's just a really useful thing to know. So kind of the general case is the following. General case. So imagine I have q of, let's say, alpha is equal to 0. So this means alpha is not in the domain. And I want to know what type of problem is it. Is it an infinite discontinuity? Is it a removable one? So we take px over qx and factor x minus alpha out as much as possible. Now again, this could be very difficult in general. You'd have to do long division, all that kind of business, but doesn't matter. Imagine we've done it. So we're trying to understand the theory here, like what the general shape is. Don't really think about computation at the moment. Think about what is the story going on. So write it as p1x, and then let's do x minus alpha to the power m on top, let's say, divided by q1x with an x minus alpha to the n on the bottom. So what we're doing here is factoring out x minus alpha as much as possible. So factor out x minus alpha as much as possible. You may not have anything for the top though. Just like before, there may be no factors x minus alpha. So this m here is greater than, it's always got to be positive because they're polynomials, but it's going to be, or non-negative, it's going to be greater than or equal to 0, could be 0, but the n, because of the fact x or alpha is a 0 of q, n has to be, there certainly has to be at least 1 factor. So here's the story. It's very simple. You just look, is it top heavy or bottom heavy? And that basically is going to tell you what's going to happen. So if we have, so if it's strictly more on the bottom than the top, strictly more on the bottom than on the top. So if I have m strictly less than n, so there's strictly more terms on the bottom than the top, then I get an infinite discontinuity. And if the opposite extreme is true, if m is greater than or equal to n, so it could be equal, then I have a removable discontinuity. So it just looks like a hole. So just to reiterate, the possible graphs here, so the infinite discontinuities is kind of a bit more difficult, but if I have my alpha here, the possibilities are, well, there are kind of 4 possibilities. It all depends. You could be coming in like this, you could be coming in like this. See, this is information that we can't really get at right now. We know it'll look like that roughly, but it could be any of these. So these are the possible graphs. This line is often called a vertical asymptote, but we're not going to talk about that really. It's something for calculus. So this is possible graphs. And for the removal one, much simpler. This is your alpha. It's all going along fine, and there's just a hole like that. So that's the general case here. That's the general story. It's really useful to know it before you go into calculus, just so that you can be kind of aware of the basic story. When you do calculus, the process of finding infinite discontinuities, all these kind of things, is much more broad than just rational functions. This is something, again, that high school can mess with you about, because maybe you've learned about infinite discontinuities, vertical asymptotes, something like that at high school, but very frequently it's only from the perspective of rational functions, which is just far too limited. So when you learn this at university, you'll learn it with respect to all functions, and this will be a special case of it. So it's just, again, something to be aware of when trying to relate this back to your prior knowledge if you've seen it before. So let's do one last example just to check all this. So, example. So we'll do one that all the factorizations are easy. So let's imagine I give us f of x is equal to x squared minus 5x plus 4, all divided by x squared minus 3x plus 2. So what's this? What's going on? To the top, it all factors fairly easily. This is x minus 4, x minus 1, divided by, what is it? X minus 2 times x minus 1. So before you rush in and cancel this stuff off, no, we need to be much more careful. So let's do x-intercepts first, shall we? So we might as well do them because we've been doing them all along. So x-intercepts, to start off with, we need to have x minus 4 times x minus 1 is equal to 0. This is if and only if x is equal to 4 or x is equal to 1. Now we've got to be a bit careful. Unfortunately, so if this is px and this is qx, what do we see? Well, if I feed 1 into q, that gives me 0. So that's going to be no good because I'd have 0 over 0. But if I feed 4 in, that's not equal to 0. So these things all put together tell me what? They tell me that the x-intercept only happens at 4 because I can't have 0 divided by 0. It's the only one. Easy mistake to make if you're not careful. Let's do domains. So then we need to look at the base being 0. So not the base, I mean the denominator. So x minus 2 times x minus 1 is equal to 0. So clearly we've just seen part of this. This is if and only if x is equal to 1 or x is equal to 2. So I know what the domain is. So the domain is all x such that x is not equal to 1 and x is not equal to 2. So I suppose if we want to write this in my interval notation, open interval from minus infinity to 1, then 1 to 2, all open, then union 2 to infinity. All open, you don't want to include 1 or 2. Okay, what are the nature of these discontinuities? So let's go through both of them carefully. So let me just grab this again so we can see it. This is my function. So let's do x is equal to 2, shall we? So my function is what? Well, it would be x minus 4, x minus 1, okay, divided by x minus 1, x minus 2. X minus 2 is what I care about here, right? This is my x minus alpha from the story. So that's what? This is power 1 down here, and I suppose there's no factor on top, so I could write in x minus 2 with power 0 if I want to kind of really hammer this home. But what's true? Well, that means it's bottom heavy. So there are more factors, strictly more factors on the bottom than the top. So that means we get an infinite discontinuity. At x is equal to 2. So it's going to be something bad happening as I come in from either side. Again, to really know exactly what happens on either side, you need to do more work with calculus ideas. But for us, we know it is bad. Well, x is equal to 1. This is x minus 4, x minus 1. So this is my function. What is it? Yes, x minus 2, x minus 1. But now that's obviously a 1 and a 1. And of course, 1 is equal to 1. So now it's not bottom heavy. It's the same on top and bottom. This is a removable discontinuity. Okay, at x is equal to 1. So it would be a hole in the graph. And the real reason for that is because if I'm away from 1, I can cancel this off and cancel this off, and then there's absolutely no problems at all, right? What's left doesn't have any issues. Whereas in the top one, I cannot cancel off the x minus 2 to get rid of it. It's not removable. It's always going to be a problem. Okay, so that is really all we can say in general. Things like, I mean, range, 1 to 1, all of these things, order even, they're pretty complicated. They're not easy to read off from a rational function, and they require more sophisticated analysis of functions, which has to wait until calculus. But Xintercepts and domains we can deal with, and especially interesting, we can classify two types of problems that could happen in the domain, namely some sort of infinite discontinuity, where the graph goes haywire as you get closer and closer to my point, or a removable one where it's kind of totally fine, it's just like the point has been removed.